Hello everyone. So let us start today's session. This is session number 11 and the today's topic is line capacitance calculation. In the last class we have gone through the line inductance calculation. So briefly first we will go through the revision of the last class. So we have seen that total inductance due to solid conductor at a distance d is given by this expression and if you if you want to calculate the inductance of single phase 2 wire system, then it is double of the solid conductor, that is 4 into 10 to the power minus 7 ln d divided by r dash, where r dash is 0.8877 into r, that is self GMD of the conductor or GMR of the conductor. Now if you want to see the find the inductance of three phase 3 wire with equal spacing, then the same expression, similar expression will come as of the single conductor, that is given by this lower expression, and this is per phase. And for the single phase 2 wire system, this is also called a loop inductance, so that's why I represented it as like per circuit. Now we have seen that in the last class we have seen that why we do bundling of conductors. Generally, we do bundling conductors to increase the GMR of conductor such that we can increase the power transfer capacity of line, and we can reduce the corona losses, reduce the radio interference. There are so many advantages of bundling of conductors that we have seen in the last class. And now if you want to find the equivalent inductance due to bundling, here in the place of R dash you have to replace it by GMR. So you have to find the GMR of the conductor first, then you can use the same expression as the previous one. And then we have seen the transposition of transmission line. We do transposition of transmission line to balance the system. Generally what happens is that this we are having unsymmetrical tower configuration, so that leads to unequal line inductance, and that will happen to having unequal voltage drop across the line, and whatever we are sending the line voltage, we will get the unbalanced voltage at the receiver side. Therefore it is necessary to do transposition of line, and in transposition of line we divide the line into equal number of distances such that each phase conductor will place in the other phase conductor, so that they they experience the same distance with respect to each other, and finally we will get the balance system. And in the transposition of conductors we can also do bundling of conductors. If that is bundle, then in the case of r dash we will replace it with GMR. So that's all about the last class. We have seen about the inductance of solid conductor, we have seen the inductance of single phase system, we have seen the inductance of three phase wire system with symmetrical spacing or equal spacing, and we have seen the bundling of conductors and transposition of conductors, how we can find the inductance. For that case also we can see that all the expression are similar, and just we have to put the similar expression in all of these. Just keep in mind this all expression, inductance expression have the value comes as per phase. Now we will see the electric field and potential difference that is very necessary for the capacitance calculation. We all know that electric fields originate at positive charge and terminate at negative charge, and this current carrying conductor contains charges. Therefore, this electric field exists around a current carrying conductor. And if we see the definition of capacitance, it is the ratio of charge on the conductors to the potential difference between them. And similar to the, we have applied the Ampere circuital law in the inductance calculation, we will apply here the Gauss theorem to find the electric field intensity at a distance y from the active conductor. And this relation comes as E y is equal to Q divided by 2 pi epsilon y volt per meter. The unit of electric field intensity is volt per meter. So here Q is the charge on conductor per meter length. So that's why Q is the charge on the conductor per meter length, and y is the distance in meter from the axis of conductor, and epsilon naught is the permittivity of Fourier space, and this value all we know that T of Fourier space, this value is 8.854 into 10 to the power minus 12 Fermi per meter. So basically this requires for the capacitance calculation. And now if we see the voltage difference between this point x1 and x2, if we are having solid cylindrical conductor which have uniform charge throughout its length, then we can see that how we can find the potential difference. We can integrate over from d1 to d2 e to e by dy, and we can find electric field intensity from the Gauss law, and we got this one. And here by is missing, sorry, 2 pi epsilon naught by dy. So we will get this potential difference between point 1 and 2. And here V12 is the voltage at x1 with respect to x2. V12 is the voltage at x1 with respect to x2. And this value is positive when q is positive, and d2 should be greater than d1. In other way, you can also say that x1 is at the higher potential than x2. So basically we require this potential difference expression for finding the capacitance calculation. For deriving the capacitance value, we use the, we all know that q is equal to cv expression. From that expression we can get capacitance calculation as the ratio of charge divided by the potential difference. So I have directly written down this capacitance of single phase line, but you can go through the derivation of this capacitance calculation. If you see the capacitance of single phase line, we are having two conductors in which the current is going inside the conductor, and in another conductor it is coming out. So both each having radius as r1 and other having radius as r2, and they are displaced from each other by d distance. This line to line capacitance can be written as pi epsilon naught divided by ln divided by r1 r2, and the ratio is Fermi per meter. And suppose if this r1 r2 is equal, and then we can take it as r. So this is can simplified by this C12 is equal to pi epsilon ln into d divided by r, Fermi per meter. So this equation gives the line to line capacitance between the conductors, and this is also very important expression. Now if we want to find the line to neutral capacitance, then how we can find this line to neutral capacitance. So we all know that this is very important for the transmission line modeling. So therefore we can say that if this line to neutral line, we have found this line to line capacitance, then there must be at some point where this electric field intensity goes to zero, and at that point potential will be zero. So this we can represent as neutral point, and we can say that the potential difference to neutral is half of this V1 V2. Therefore this capacitance will be get double to that of the capacitance between 1 and 2 point. All okay. So this will be C1n is equal to C2n is equal to 2C1 C2, because this potential difference to neutral is half of V1 V2. Therefore capacitance value will get doubled, and we will get this line to neutral capacitance value. So till here any doubt you can ask? Till here we have gone through. I think all of you joined late. So first we have revised the things that we have discussed in last class, and then we come through this electric field and potential difference concept, and this is used for the capacitance calculation derivation, and I have written down this capacitance derivation directly, and from this capacitance of single phase line we can find this line to neutral capacitance using this concept. This one is C1n, C2n is line to neutral capacitance, and this expression is very important. In the inductance calculation, the expression is coming like this: L is for uh, for a solid conductor is 2 into 10 to the power minus 7 ln d divided by r. Here for capacitance we are getting like this. So both are very important in the inductance and capacitance calculation. Now we are going to solve the problem based on this expression. If you have any doubt or anything you want to ask, then you can raise your concern. So here the question is that the horizontally placed conductors of a single phase line operating at 50 Hz are having outside diameter of 1.6 centimeter, and a spacing between centers of the conductor is 6 centimeter. The permittivity of free space is 8.854 into 10 to the power minus 12 Fermi per meter, farad per meter. The capacitance to ground per kilometer of each line is. So how you can find this? So this question is from GATE 2014. It is of 2 marks. Here we are given with this outer diameter as 1.6 centimeter. So radius will be 1.6 divided by 2, that is 0.08, sorry, 0.8 centimeter, and permittivity is given epsilon naught is 8.854 into 10 to the power minus 12 farad per meter. All of you try just try to solve problem with me, and you can type your answer in the chat box. So applying the expression C is equal to 2 pi epsilon naught divided by ln d divided by r. So just you have to put all these value and get the answer 8.854 into 10 to the power minus 12 farad per meter, and their ln is d is given as 6 centimeter, so it will be 6 centimeter. So unit of d and r should be same, so that it gets cancelled out. 0.8, sorry, here it is meter. Big mistake. This the specimen center of conductor is given as 6 meter, not as 6 centimeter. So we have to convert r unit as 0 in meter. 0.8 into 10 to the power minus 2 meter, 8 into 10 to the power minus 2 meter, and this will come as 2 pi into 8.854 10 to the power minus 12 ln d divided by r will come as 6.62. This will come as 8.4 into 10 to the power minus 12 farad per meter. So what will be the correct answer? Anyone got the answer?
Yes, sir.
Yes, Harsudan. What is the correct answer? Hari Harsudan. Which option will you correct? So if we don't read the question directly, then we may do a mistake, because in the question it is asked about this per kilometer. So the question is asked that capacitance to ground per kilometer.
Sir,
Yes,
sir,
yeah.
sir, in formula, not pi the epsilon divided logarithm of d by r only, sir. But in question you put 2 into,
Where?
sir, in before slides, capacitance is equal to formula, sir.
In previous slide. I'm not getting your doubt.
Sir, in previous slide, you see you put capacitance is equal to pi, this formula only, sir.
Is it 2 pi epsilon not?
Ah, okay, sir.
Yeah, correct. So remember this expression. So why we have used this expression? Because it is asked about the with respect to ground. That means you have to calculate the line to neutral capacitance. This one only. If they have not given this reference, that in there you have to calculate the line to line capacitance. So it is asked about the line to neutral capacitance. And another thing is that it is asked in
Okay.
per kilometer. So in per kilometer you have to it will come as 10 to the power minus 9 farad per kilometer. So correct option will be B. 8.4 into 10 to the power minus 9 farad. And since kilometer is given in question, so they have not written down per kilometer. So if there is no doubt, so we can move to the another part. Now we will see the capacitance of three phase line. So if suppose if these are unsymmetrical spacing, so for balancing the system, we use the we do the transposition of transmission line, and transmission of transmission line leads to the equal capacitance of each phase. Therefore, by deriving this expression, you will get this similar expression as the previous one for the single phase line. So the capacitance per phase to neutral of the transposed transmission line is given like this. So just similar to the previous, whatever we have seen in the inductance calculation, that we do the transposition for balancing the system. If we don't do transposition due to unsymmetrical tower configuration, we may get the unbalanced system. What if we are sending the balanced voltage at the sending end side, but due to different line inductance, we are getting the unequal voltage levels. So it gets unbalanced system. And similar here, if this is if we don't do transposition, then we are getting the unequal capacitance value for each phases. So that leads to unbalanced system at the output also. So this you can write this capacitance per phase expression like this for transposed transmission line, and here GMD is written like this. GMD will be DAB DBC DCA to the power 1 divided by 3. And suppose these are having equilateral spacing or equal spacing, that means DAB is equal to DBC is equal to DCA. You can assume it as D. Therefore, you will get the capacitance per phase to neutral will be, in the place of GMD, it will come as D. And one more important thing we have noticed in capacitance calculation, that we are not using R dash, right? Like see here, we are not using R dash. But in inductance calculation, we are using R dash, that is self GMR of conductor, self GMD of conductor or GMR of conductor. So just keep it in your note that in inductance calculation, we assume the R dash, while in capacitance calculation, we take simply as radius of conductor, not the GMR of conductor or self GMD of conductor. This is because anyone know the what is the reason behind this? Harihar, Sudan, Biraya, Pratik. Only three people are there. So
No,
you
sir.
anyone can tell the reason behind this. We have taken this R only in the capacitance calculation, while inductance calculation we take the GMR of conductor. So this is because if we see the in capacitance, then we can see that electric field inside the conductor is zero, right? But in inductance, we have seen that flux linkage inside is not zero. It is coming as 1.5 into 10 to the power minus 7 Fermi per meter. So that is the reason. In the inductance calculation, this R dash is coming. That is, sorry, here I have to, here I have to write R dash. So R dash is e to the power 1 divided 4 into R, that is coming at 0.77 88R. So this is inductance expression and this is capacitance expression. So only major difference is that in inside the ln terms we are using r dash, but in capacitance calculation we are not using r dash because electric field inside the conductor is zero, but the flux linkage inside the conductor is not zero. That's why this extra term is coming, e to the power minus 1 divided by 4. Correct? This is very very important and one of the favorite question asked during the Viva voice examination. So we have seen till this part. Now we will see the bundling of conductors. So uh, we have seen the bundle conductors in the previous class also. Only difference is that in the calculation of GMR, all things will remain same. Irrespective of R dash, we are going to use the R only, the actual radius of the conductor, not GMR of each conductor. That is, R, we are not going to R dash of each conductor. So GMR of bundle conductor calculated earlier for the inductance calculation with the exception that the radius R of R each conductor is used. So I have written down here. This is very very important and you can find this GMR of for two conductors like this way, and for three conductors each named as 1 to 3 and all are equally displaced. This is becomes like equilateral triangle. So therefore GMR will be R into, and it is displaced from the conductor as d and the conductor as d, so r into d square to the power 1 divided by 3. And for quadruplex, that is it is having four conductors and all are equally displaced by distance d, so GMR of one conductor you can find like this, taking as radius of first conductor and measuring the distance of other conductors with respect to that conductors. So you will get like this. If you are finding the GMR of one conductor, then you will get R into, it is distance at D from second conductor, and it is a distance D from third conductor, and it is distance root 2 times of D from fourth conductor, and you will get this expression. And here it is a mistake, so it is R only, not R dash. I hope all of means everything is clear. So similarly, we can find this for bundle conductors. In the place of R, we will use the GMR to find this capacitance per phase. Capacitance per phase with respect to neutral point CAN, that is 2 pi epsilon naught divided by ln into GMD divided by GMR farad per meter. Now we will see the capacitance of single phase line considering the effect of earth. So if you consider the effect of earth, that leads to increase in the capacitance value because earth is have a enormous amount of charge also. So just taking it as what the amount of charge inside the conductor, just take it as equal amount, just opposite to the that of charge, it is placed at equal distance beneath the earth. So from that way, using the mirror image concept, you can find the capacitance of line considering the effect of earth. So the earth affects the calculation of capacitance of three-phase lines as its presence alters the electric field lines. If the effect of earth is taken into account, this capacitance value increases. So this is important point. Now, if with this height of conductors placed on a transmission towers is much larger than the spacing between the conductors, therefore this effect of earth can be neglected for capacitance calculation, especially when balanced steady state operation of the power system is considered. So if this point says that this suppose distance of tower is much larger than the distance between the conductors. That is distance between the conductors is d, and h is the height of the conductor from the ground. So if this is larger, then this is neglected. Therefore, this Cn will become equivalent as previous one. You can d square divided by 4h square is a small. If d square divided by 4h square small, then the effect of earth, then the effect of earth line capacitance is negligible. But for unbalanced operation, when the sum of three phase line currents is not zero, then we have to consider the effect of earth there. So keep in mind these important points. Now we are going to solve one problem. So all of you just take your pen and paper out and solve parallelly with me. So here this figure shows a completely transposed 50 Hz to 50 kilometer long three-phase line has flat horizontal phase spacing with 10-meter spaced adjacent bundle conductors. So this distance is given as 10 meter, and this is bundle conductors having two conductors. So this is for one phase. You can take it as A and A dash, and we can take it as B and B dash. These are subconductors of a bundle conductor, C and C dash. If the radius of each subconductor is given as 1.2 centimeter, so this radius is given as 1.2 centimeter. 1.2 centimeter, that means 0.012 meter. And the line voltage is given as 220 kV. Determine the charging current per phase. We have to find the charging current per phase. So here this new term comes, and the total reactive power in MVR. So for finding the charging current, we need to get the capacitance value of conductor. So for finding, we all know this capacitance value of capacitance per phase with respect to neutral point is that 2 pi epsilon naught divided by ln gmd divided by gmr farad per meter. So first we need to find this gmd and gmr. So let us first see the gmr. So all conductors of phases are identical. So gmr will be like, for we have considered the a phase, so we can write that daa dash, sorry, first we take with respect to itself daa only, and then daa dash, and then da dash a, then da dash a dash. So how many terms inside the conductor? There are four terms inside the conductor, so it will be 1 divided by 4. So what is the value of daa? Can anyone tell what is the value of daa?
0.7788 into D
0.
7788.
No, no, da, as I have told you that you have to not consider this r dash value, e to the power
Okay.
minus 1 by 4. That is we have to consider in the line inductance calculation. So you have to simply take here R only. So this will be R,
I got it, sir. Okay. Okay.
and dA dash will be
Uh, D, sir. D, distance between
a small d or capital D.
small d, small d.
Yes, 0.4 meter. So this is D only, and dA dash A is also D, and daa dash is with
R,
respect to
R.
R only. Correct. Very good. So this is 1 divided by 4. Therefore R into D, 1 divided by 2, and this will be, can write, we have R value as 0.012 into 0.4. So this is 0.0693 meter. This we got GMR of conductor, that is bundle conductor. If this is not bundle conductor given, then we directly we have given with radius of conductor, then we have to use this R value only. Since they are bundle conductors, so we have to find the GMR of phase conductor. Now for finding the GMD, here you can see that the distance between subconductors is changing. But if you approximate the distance like as D only, that is given by 10 meter or 10 meter. But if you see the distance between subconductors, it is changing. So we will see the both methods, that we will see the exact method and we will see the approximate method, that what is the difference in the self GMD for the conductors. First we are going to see the exact method, that will, that there we have not taken any approximation. So for finding the D equivalent, it is DAB, distance between A and B conductors, A phase and B phase conductors, and DVC, distance between B phase and C phase conductors, and DCA is distance between C phase and A phase conductors, 1 divided by 3. So this is the expression for GMD. It is not better to write the equivalent. This is the GMD. Now DAB, like we can find the distance between DAB, we can see that between the subconductors this distance is changing. So like suppose this DAB we can write, and then we are having this DAB dash, and then we are having with DA dash B, and then we are having with DA dash B dash. So like this is A dash and B dash. So this distance is given as 10 meter, and this distance is given as 0.4 meter. Now tell me, what is the distance of DAB? Anyone
10
can?
meter. 10
Yes,
meter.
yes, correct. Very good. DAB dash, AB dash. Tell Harishyam.
10 meters, sir.
DAB dash. This distance and last point, 10.4,
10.8 meters. 10
10,
point.
10.4, and DA dash will be from A dash to B, 0.4 bit will get subtracted
9.6 meter.
9.6, and A dash B dash will be same 10, 1 divided by 4. So this is coming as 9.995 meter. Since B and C phase conductors are also similar to DAB, so this is equal to DAB, that is 9.995 meter, and DCA we have to, in the place of 10 we will just write with respect to 20. So like DCA, DCA dash, and DCA dash, and DCA dash. So similar to this one, it is like little bit far. So it is like 20 meter, and this distance is again 10 meter, sorry, zero point 0.4 meter, and this is A dash, C dash. So DCA will be 20 meter only. Here we have to write 1 divided by 4, and DCA dash 20 minus zero point 0.4, that will be 19.6, and DC dash A, that is the most far point, so it will be 20.4, and DC dash A dash will be again 20. So this will become as 19.997 meter. Therefore GMD will be 9.995 point into 9.995, 19.997 to the power 1 divided by 3, that will come as 12.594 meter, that is approximately coming as 12.6 meter. Correct. Now one may can directly find, because they may use this 10 meter ratio directly. So like we can write this as GMD approx. GMD approx value will be DAB, DBC, DCA to the power 1 divided 3, that is 10 into 10 into 20 to the power 1 divided by 3, that is coming as 12.599 meter, that is coming as 12.6 meter. So you can see that these both are coming equivalently equal. 12.594 meter, here we are getting 12.599 meter. So you can write 1 point approximate value of GMD can be calculated quickly, can be calculated quickly, which is very close to exact value. Now we have found this both GMD and GMR, so we can directly apply this expression, line to neutral capacitance 2 pi epsilon naught divided by ln GMD divided by GMR farad per meter. So it will be 2 pi into 8.854 into 10 to the power minus 12 divided by ln. GMD is 12.6 and GMR we have found 0.0693. Anyone got this capacitance value? So it will come as, this value come as 5.6, 5.2. So this will be 10.692 into 10 to the power minus 12 farad per meter. So we have to find the exact value because we are going to find this charging current. For charging current we have to find this, multiply with length. So let us first convert into kilometer. 10.692 into 10 to the power minus 12 farad per kilometer, and this line distance is 250 kilometer. It is given in the question, so multiply with 250, 10 to the minus 12 into 250 is farad, so it will be coming as 2.673. Sorry, it is minus 9. So you should tell if you see any wrong calculation here. So 2.673 10 to the power minus 9 farad. So it is also not, it is 2673. So this is 2.673 10 to the power minus 6 farad. This is line to neutral capacitance. Now we need to find this XC. So XC, how can find? XC will be 1 divided by j omega CAN. Therefore mod of XC you can write taking the magnitude only, that will be 1 divided by omega CAN. So from there we can find this line charging current per phase. Line charging current per phase will be, IC will be VN divided by magnitude of XC. So it will be omega CAN VAN. So putting all these values, 2 pi into 50, CAN is given as 2.673 into 10 to the power minus 6, and VAN is given as, we can write here, so 2 pi into 50 into 2.673 10 to the minus 6 220 divided by root 3. It is in kV, so multiply with 3, that is ampere per phase. So you will get this expression as 106.66 ampere per phase. So therefore 0.106 kilo ampere per phase. Till here any doubt? Now we need to find this reactive power. It is asked about total reactive power in MVAR supplied by the line capacitance. So for finding the reactive power, by this expression QC three phase, that is 3 into VAN square divided by XC mod XC. So 3, if take XC as top, VAN square. So put all this value 3 into 2 pi into 50. CA is given as 2.673, 10 to the minus 6, that is 220 divided by root 3 into 10 to the power 6 because it is kV. So putting all this value will get 40643789 var, that is 40.64 MVA var. So this is the value, this is the answer. In this problem we have covered all the part, like you may need to, they may ask this line charging current per phase, so you have to use this one. If they ask total line charging current, then you have to multiply with root 3. There you have to take this VLL term, not phase voltage. And generally they asked in per phase, so we will apply this expression only. And we have seen this how we can calculate the GMD and GMR if we are having this bundle conductors. And now we are coming to the last uh, problem. So you have to tell about this. We are just going to revise the line inductance calculation and line capacitance calculation. So I want to hear from your side that which of these statements are true or false. First part is that the internal inductance of a solid cylindrical conductor depends on the radius of a conductor. This is true or false? Anyone
True,
can
sir.
tell. Hurry.
False, sir. False. False.
Okay, one.
Option A, false.
Biraya is saying false,
Yes,
and
sir.
anyone says
Yes.
true. So yes, correct. Viraya Nagula, correct. This is false. Inductance of a conductor of a solid cylindrical conductor depends on the radius. And this is false because we have seen that L internal inductance is half into 10 to the power minus 7 Henry per meter. So this expression we got. So they know R term comes here. So that's why this is false. And second option is that in terms of line to line capacitance, line to neutral capacitance is half. It is
True,
true,
sir.
true or false?
True. True. True, sir.
Read the question carefully. Are you sure, Biraya and Biraya Nagula and Hari Sudan? We have seen here. I think you have not read the question carefully. In terms of line to line capacitance, line to neutral capacitance is half. It is also false. We have seen C1N or C2N is equal to 2C12.
Okay, okay. Got it, sir. Sorry, sir. Sorry, sir.
Yes. So this is we have found the capacitance between 2 points, two conductors of single phase wire. So 1, 2, and this is neutral point. So we can having one point where this electric field gets zero, where this potential is also zero. So therefore you can say that like here we have shown you. I have shown you. Since the potential difference to neutral is half of Va2, so therefore capacitor gets double. Vn2 is like you can write V1n or V2n is half of V12. So this capacitance get double because Q is equal to CV. If this is reducing by half, then V have to increase. This is reducing, so C have to increase. So that's why. And remember this expression only. This neutral with respect to neutral, because generally they asked this capacitance calculation with respect to neutral point only. So remember this expression only. If this is for single phase wire, not bundle of conductor, then you have to only use R in place of GMR. And if it is asking about the line to line capacitance, then 2 will be vanished out. If it is asking about line to neutral capacitance, then 2 will come here. So this is, I think you have to remember this expression only, so that you can correlate the terms, because they generally asked this line to neutral capacitance, not ask the line to line capacitance. Now the third point is that bundling of conductor reduces the corona loss. This is true or false? This is very simple. Pratik, Nagula and Hari Sudan.
True, sir.
Yes,
True, true.
yes, true. Bundling of conductors has whatever the positive points that all comes into bundling conductors. First, it increases the GMR, so that line inductance increases. uh, Sorry, it increases the GMR, so that line inductance decreases. That's why it increases the power capacity, power transfer capacity of line, and it reduces the corona losses, and it reduces the radio interference also. So all are the bonding advantages of bonding of conductor. Bonding of conductor leads to increase in the geometric mean radius of the conductor. So this is all for today's class. So today we have covered these characteristics of transmission line, that is line and capacitance calculation. In the next class, from the next class, we will see the modeling of transmission, modeling of short transmission line, medium transmission line, and long transmission line.
Thank
Any
you, sir.
doubt, any query? Thank you all for attending the session.
Thank you, sir. Thank you.